Hello, welcome to EE323, Lecture 16. Today I'll be talking about the difference amplifier. You can find this in your book in section 2.4. All right, let's get started. So we're talking about a difference amplifier today, and a difference amplifier is an amplifier that amplifies the difference between two signals. The first question we'd like to answer is why? Why do we care about amplifying the difference between two signals? I'll start with just a quick example. Suppose we have an amplifier. Just draw it as a triangle. And we have some signal coming in, some sinusoid-like signal. Now, that sinusoid, let's assume that it's going to get corrupted by noise. So we get some noise that's superimposed on top of our sinusoid. And this is noise that couples in from any of a variety of sources. And this is very practical. This happens all the time in the real world. At the output, what you would see is an amplified version of your sinusoid, right? But also the noise is going to get amplified as well. So any noise going into our amplifier gets amplified by the amplifier. Now, alternatively, what we could do is take two amplifiers. I'll draw it like this. And now, what we're going to put in the input here are signals that are 180 degrees out of phase. So one might have a sinusoid like that, and the other has a sinusoid like that. So our inputs are out of phase. Now, let's assume the same noise comes in and corrupts our signal and corrupts our signal. So at the output then of our amplifiers, what we're going to have is an amplified version of the input, and amplified versions like that, and we're also going to have the noise that's amplified on top of the signals. But then here comes the nice trick. If we take these signals and we combine them, except but they're 180 degrees out of phase. In other words, we're taking their difference. What we see at the output then, if we just take the difference of these two, is that the noise is gone. And that's because the noise contributed equally to both signals in the beginning. Noise got amplified, but now when we subtract these two signals, and we're subtracting because one is out of phase with the other, the noise disappears because it's the same on both sides. So this is called differential signaling, and this is used all the time in practical circuits, especially on integrated circuits. So now let's go to a few definitions. First of all, we can write here, we can use some terms, that the output voltage of an amplifier is the differential gain, AD, times the differential input, VID, plus the common mode gain, ACM, times the common mode input. And so what do we mean by that? The differential mode gain, VID, is equal to the difference between our two input signals. Call it VI2 minus VI1. The common mode gain, the input common mode signal is equal to the average of our two input signals, VI2 plus VI1. So if we manipulate this and solve for VI1 and solve for VI2, what we get is that VI1 is equal to a common mode signal minus VID over 2. This should be VI. And VI2 is equal to the common mode signal plus VID over 2. So if we were to draw the circuit diagram for this is shown on the right. What we have here is a common mode input that goes to both sides. And then we have minus VID2 for VI1 and plus VID2 for VI2. So you can see that VI2, for example, is equal to V common mode plus VID over 2, and that gives us VI2. All right, let's do a few examples to make sure that we understand this. Suppose we have one input voltage that is 2 volts, VI1, and VI2 is 5 volts. And we could write the VI differential is equal to VI2 minus VI1, and that would be equal to 3 volts. And VI common mode is equal to 1/2 of 5 plus 2, which would be equal to 3.5 volts. Another example on the right here, suppose VI1 is sine omega t, VI2 is 10 sine omega t, then VID is equal to VI2 minus VI1, which would be equal to 9 sine omega t, and VI common mode would be equal to 1/2 of 11 sine omega t, which would be equal to 5.5 sine omega t. And then this final example here where VI1 is minus sine omega t plus 10, VI2 is plus sine omega t plus 10. We can see that VID, which is the difference of these, is just 2 sine omega t, and VI common mode is equal to 10. Now this turns out to be an important example where we have a common mode voltage and equal but opposite time varying components. So if we were to draw this, what would this look like in time, this input? If we were to draw voltage as a function of time, what we'd have is one input that would look like this. So it's a sinusoid but offset by 10. So this would be something like 10 volts. And then we'd have another sinusoid. Looks like that. And so what we prefer from our amplifier is we want the signal of interest is amplified, right? We want the signal of interest, which in this case would be our time varying component sine omega t. We want that to be amplified, and we want the rest of it, the common mode signals, to not be amplified. So ideally we want our common mode gain to go to 0 while our differential signals are amplified. So if the common mode goes to 0, this gets rid of the common mode signals, right? And we want a differential mode gain. And so to quantify this, people have come up with this term called common mode rejection ratio, or CMRR. And this has multiple definitions. We'll talk about this more throughout the semester. But one definition is typically expressed in dB, 20 log of the differential mode gain, the absolute value of the differential mode gain over the absolute value of the common mode gain. All right, so if we want to amplify the difference between two signals, how do we do that? Right? We want to use differential signaling, so we can then we need an amplifier that's going to amplify the difference between signals for differential signaling. All right, so what do we know so far? How do we go about making a difference amplifier? That's the next task here. So what do we know so far? We know two configurations. We have this configuration on the left, which we know is an inverting amplifier. We have a configuration on the right, which is a non-inverting. And we have the gain for each. It turns out, right, if we just take these and add them together, what do we get? What we get is that V out is equal to VI2, which is the non-inverting input, minus times 1 plus R2 over R1. So this is from the non-inverting. And then if we add this with the output of the inverting, we get a negative sign from the inverting amplifier times VI1 times R2 over R1. Now this is really actually close to what we're looking for, right? What we're looking for is an output that's proportional, that has a gain, that the output is proportional to VI2 minus VI1. And we're actually pretty close here, so this will give us some hint about how to make an a difference amplifier. So if we try to combine this inverting with the non-inverting, and we try to put those into one circuit, what we get is something that looks like this. So we have an input VI1 going into the negative terminal. This is like the inverting path over here. And then we have VI2 going into the positive terminal, and this is like a non-inverting path. And this might get us close to making a difference amplifier. So let's examine this a little bit more closely. So how would we figure out the output of this, something like this? Well, we have two inputs, linear circuit, so we're going to use superposition. So the first case, what we're going to do is look at VI1, right? And so to do that, we're going to take our amplifier and we're going to ground VI2. So we're going to have R4 that goes to ground. We're going to have R3, which goes to ground. And then we're going to have our input here, VI1. This would be R2 and R1, and we'll call this V out 1. So we can write by inspection, because R3 and R4 are grounded, there's no current, therefore the positive terminal is also grounded. So we can write by inspection just based on the idea that this is a inverting amplifier. We can write that V out 1 is equal to minus R2 over R1 times V in 1. All right, now let's look at what happens when we look at the input VI2. So in this case, we draw our amplifier like so. We have R3 and R4. VI2. Now the negative input with R1, this is grounded, right? VI1 goes to 0. And we have R2 and V out 2. So in this case, we can write that V out 2 is equal to R4 over R4 plus R3 plus VI2 times 1 plus R2 over R1. Well, how did we get that? First thing we need to figure out is what V plus is. If we can figure out V plus, we can treat this like an inverting amplifier, a non-inverting amplifier. So V plus, in this case, this is a resistive divider between R4 and R3. So V plus is just R4 over R4 plus R3 times VI2. So this portion right here is just V plus, and then that gets multiplied by the non-inverting gain of 1 plus R2 over R1. So to truly make a difference amplifier, right, what we'd like then is that the gain here, it's this R4 over R4 plus R3 times 1 plus R2 over R1. We'd like that to be equal to R2 over R1 from the inverting case. So we'd like R2 over R1 from the inverting amplifier to equal R4 over R4 plus R3 times 1 plus R2 over R1. If we can set those equal and figure out values that make those equal for R4 and R3, then we'd actually have a difference amplifier. All right, so how do we do that? Well, so we want V out 2 over VI2, which is equal to R2 over R1, right, to equal this value. So we want R2 over R1 to equal R4 over R3 plus 1 plus R2 over R1. as I just described here, so that the magnitude of the gains are equal, even though we're going to have opposite signs, which is going to give us a difference. So if we manipulate this equation a little bit, we'll find that we get R4 over R4 plus R3, and we move this term here over to the right side. Right, this would become R1 plus R2 over R1. Move it to the right, and we get R2 over R2 plus R1. Now, if I were to divide each term here by R4, and each term here by R2, in other words, just multiply numerator and denominator by 1 over R4 on the left and 1 over R2 on the right, what we end up with is that if we set R4 over R3 equal to R2 over R1, then this condition becomes true. So that is the key, is that the ratio of these resistors here, R2 to R1, must equal the ratio of R4 to R3 for this to make a true difference amplifier. All right, so here's our difference amplifier. We're going to try to confirm now that this actually works. So the first thing we'll do is take the input from VI2, and this is just straight from the previous slide. VO2 is R4 over R3 times VI2 plus 1 plus R2 over R1. We can manipulate this a little bit and multiply by 1 over R3 and on this, right? So we're dividing all these by R3. And we get the second equation there. And now, if we substitute R4 over R3 equal to R2 over R1, what we get is that V out 2, so we just substituted this into each of these terms here. And we manipulate that a little bit, and what we end up with here is that V out 2 is equal to R2 over R1 times VI2, which is exactly what we wanted from this positive from the non-inverting side, because we know the inverting side gives us minus R2 over R1 times VI1. So this will help us make complete our difference amplifier. So here's our final difference amplifier. V out is equal to, by superposition, V out 1 plus V out 2, which we can now write as minus R2 over R1 times VI1 plus R2 over R1 times VI2. So V out is equal to R2 over R1 times VI2 minus VI1. And this component right here, this R2 over R1, this is what we call AD, or the differential gain. And this is all assuming now that R4 over R3 is equal to R2 over R1. All right, so we figured out how to make the difference amplifier, but we still have a few unanswered questions, like what's the common mode gain from the circuit? How about the input resistance or the output resistance? Okay, so look, moving on here, let's talk about the common mode gain. So the differential gain we've just learned is R2 over R1, and to figure out what the common mode rejection ratio is, we need to figure out what the common mode gain is. So common mode gain, remember, we're applying the same signal to both terminals. If we apply the same signal to both terminals, we could recognize that the V plus node is just a resistive divider. So that gives us R4 over R4 plus R3 times the input common mode. Right? That's the voltage at V plus, which, because we have negative feedback, is also the voltage at V minus. Now that we know that, we can hopefully solve for the gain here. So to do that, we need to figure out what the input current is, because all that current is then going to be flowing into R2. So we can write that I1 is equal to V input common mode minus V minus over R1, right, which is equal to V input common mode minus R4 over R3 plus R4 times V input common mode, that whole thing divided by R1. Or in other words, I1 is equal to V input common mode times R4 over R3 plus R4 times 1 over R1. Actually, this should be R3 here, because we factor out the input common mode. If we factor that out, we end up with a term that's R3 over R3 plus R4. So next step is to find V out, and I1 would equal I2. All right, so all the current, and so we can write that V out is equal to V minus minus I2 R2, which is equal to R4 over R3 plus R4 times V input common mode minus I2 R2. And so the result there, if we solve for V out as a function of V input common mode, is the following. Now that's pretty messy. It's hard to quite understand what's going on there. So let's look at that a little bit more closely on the next slide here. So the common mode gain then, we just found out V out as a function of V input common mode. So the common mode gain is just dividing, moving the input common mode over, and we get this equation right here for the common mode. Now, it's hard to quite understand, but remember what the condition we're imposing, that R4 over R3 is equal to R2 over R1. If that's the case, this term here becomes 1, and the entire common mode gain becomes 0. So what that means is that if R4 over R3 is equal to R2 over R1, then the common mode gain equals 0. However, in practice, a common mode will be finite because resistors are not perfectly matched. It's really hard to get this to happen in practice. But if you did get them perfectly matched, then our CMRR, common mode rejection ratio, remember this is the differential mode gain divided by the common mode gain, this will go to infinity because the common mode gain tends to 0. So our common mode rejection ratio becomes really large in a circuit like this, and it's limited by how close these resistors match. All right, the last thing we're going to try to figure out here is the input resistance. So in the input resistance, to solve for that, we're going to apply a differential input voltage and measure the current, take the ratio, and we should be able to figure out what that resistance is. So for simplicity, we're going to assume R3 is equal to R1 and R4 is equal to R2. This minimizes common mode gain and makes this analysis a little bit easier. So the input resistance is just our input differential voltage divided by the current. So we notice here that we have this virtual ground right here. So this kind of sets up a nice loop for us. And we can say that VID is just the voltage drop around this loop, which is I1 R1, and we have 0 because this virtual ground, and then I1 R1 again. And so if we take the ratio, all right, we get that RID, the differential input resistance, is just equal to 2R1. Now this is not ideal. So what this means is that you need a large R1, right, for a large input resistance. However, if you have a large R1, this is going to lower our differential mode gain because remember that's proportional to R2 over R1. And so this limits how the gain we can get out of this because R2 can only be so large. The other drawback of this is that it's difficult to, with this particular circuit, it's difficult to adjust the gain. If I want to adjust the gain, I have to adjust R2 or R1, which means I have to adjust two resistors in either case. Either R1, there are two R1 resistors, or we need to adjust both R2 resistors. And that turns out to be a drawback. We'll learn about how we can potentially correct that in the next lecture. All right, that's it. Thank you very much.